I would like to start by trying to summarize where we're standing so far, what we have achieved. So at first, I tried to choose the Curie-Weiss model as our guiding example of a model of statistical mechanics on which we try to apply these PD techniques. So using this Curie-Weiss model, we saw that we were seeking this notion of solution to the PDE, which is a bit special. So we called it the notion of viscosity solution. I think I forgot to say that oftentimes in fluid dynamics, this term in front of the Laplacian is called the viscosity. So the trick that we kind of used is that we introduced a little bit of viscosity and then we sent it to 0. That's why it's called like this. So we developed this notion of solution, the notion of viscosity solution. And this notion of solution is really built around the fact that you want to satisfy the maximum principle or the comparison principle, as we have shown extensively. And because for the Curie-Weiss model, when n is finite, it wants to have this little bit of viscosity, we could show that in the limit of large n, the function indeed does want to converge to the viscosity solution. This is nice. It gives us a complete description of the limits for the Curie-Weiss model. And on top of this, there are these variational formulas under some convexity assumptions on the initial condition or on the nonlinearity. In our case, in particular, the assumption that the initial condition is convex is easy to check because our function, our free energy, is always convex by easy Hölder inequality. And next, perhaps too briefly, I mentioned what happens in the case of generalized versions of the Curie-Weiss model when we replace the nonlinearity, this function, the square function by a generic function. I was denoting it xi. And maybe we can also change the measure if we like. So using large deviations, we can still predict what the limit is. But when we try to apply the PD techniques, there was a new difficulty which I think I did not have time to do full justice for, let's say, or I was very quick, but I tried to mention that there is indeed a difficulty when you try to study models that are more general than the standard Curie-Weiss model. And in my opinion, this is a very interesting point from the technical point of view, because when you move on to study, for instance, spin glasses, and also certain models of statistical inference that are a bit more general than the one I'm going to talk about today, you face the same sort of difficulties. You have the impression that you want to solve a sort of equation with a viscosity term which seems to be having the wrong sign, and normally this is a big warning sign. It should ring alarm bells because our whole notion of solution is built around the fact that normally the sign is positive in front of the Laplacian. So fortunately, at least for the Curie-Weiss models, we found a special technique to bypass this difficulty, which is based on the fact that the functions we are dealing with are convex. So in some sense, this convexity assumption prevents the emergence of bad singularities, these counterexamples that might exist otherwise. I did not have time to explain why this is so. And after deliberation, I decided I was not going to explain this in more detail today. We're going to switch directly to statistical inference. But bear in mind that at least there is this technical option that when the functions we're dealing with are convex, we can in fact assert that we are the viscosity solution as soon as we can verify that we satisfy the equation on a dense set of points, for instance, or maybe at every point of differentiability. In fact, you can show these two statements are equivalent also. Okay, are there questions on this or comments that someone would like to make? So if not, I'm going to move today to the setting of statistical inference. So finally, we're going to discuss models with disorder inside the definition. And I'm going to focus on a specific model, not trying to address the most general possible statistical inference model. And because I'm going to focus on the specific model, in some sense, it will be analogous to the Curie-Weiss model. And so I'm not going to need the fancy convex condition, The things we have the technique we have used for the standard Curie-Weiss model is still going to be applicable for the model of statistical inference we're going to study. But again, if you want to study more general statistical inference problems, then you'll have to have this other criterion at hand. But then, yeah, as far as this, calculating the limit for energy is concerned, for statistical inference, things are by now rather well understood thanks to these techniques. Okay, so now we move to statistical inference. In the first lecture, I tried to motivate these problems by drawing a link with the problem of community detection. So perhaps I'm not going to recall this, but I gestured at the fact that, if you have, okay, maybe I'm going to say a little bit. But, so community detection is the setting in which you have individuals and maybe they belong to two communities, or maybe more communities, but let's say two. And then they create links between one another with higher probability if they belong to the same community than if they do not belong to the same community. And the only thing you're given is the observation of the links. And you wonder if you can recover information about the underlying community structure. So if you decide that you model the belonging of the communities as +1 and -1 attached to the vertices, then in some sense, the information you get when you observe a link is a noisy information on the product of these +1 and -1. Whether or not they belong to the same group, you get some sort of noisy version of this. Okay? And for reasons that are explained in the lecture notes, but that I'm not going to explain here, if you consider a regime in which the degree of each node diverges as you send the size of your system to infinity, then you can approximate this problem by a much simpler problem, which is just the observation of these pair variables. Let's say they are called x bar I, x bar j, plus noise. Okay, where the noise is Gaussian, now there's no Bernoulli complication. So yeah, this is done in this justification of the correspondence is done in the last section of chapter 4 of the lecture notes. So today we're going to just focus on this problem. I give you, let me write it. So we consider the situation in which we are given a vector of random variables. So each of them is a real random variable, and let's say they are IID and bounded. I'm going to write their law Pn. So Pn is a tensor product of a fixed measure. So we have these variables that we would like to discover, and what we observe is all of the pairwise products between these variables plus noise. So we observe let me write this y. So I'm putting a normalization. We'll see later that this is a good normalization, but maybe I'm not going to explain it right away. I'm going to write it in matrix notation. So x bar transpose plus w. W is a noise. So these are independent standard Gaussians. They are also independent from the vector x bar. And t is some parameter which I can tune. Okay, think of t as being a way for you to tune the intensity of the signal. Okay, if you like, you can call t a signal-to-noise ratio. Okay, so there is a square root of n, which perhaps I'm not going to explain exactly why that is the good normalization, but at least intuitively you see that I think it sort of makes sense that in order to recover something about this, you may be, it's not so surprising that we want to scale this term a little bit towards 0, because in the end of the day, you only want to recover n variables, and you're given n square observations. So, okay, well, I don't know. You make your calculations with information, but there's some, it kind of makes sense that you want to tune it down a little bit. Okay, so perhaps just as an extra word of motivation. So here so this is a particular example of a low rank matrix. It's a rank 1 matrix, and it's built in this specific way, x bar transpose. But in general, for instance, depending on the context you want to model, you may want to consider matrices that are not necessarily symmetric, or maybe not just rank 1. So for instance, if you think about building a recommendation system, like you have a bunch of users, maybe you're, I don't know, renting movies or books, and you have a bunch of users and a bunch of books, and you want to understand the rating that each user is going to associate with each book. Maybe as a toy model in your head, you can think that each user is represented by a small number of parameters, maybe whether or not they like happy endings, and whether or not they prefer fiction or non-fiction or whatever. Anyway, a few parameters. And then each book is also captured by a few parameters. And then the rating is a sort of combination of these few parameters. Then your kind of rating matrix is going to be a low rank matrix, which maybe you could write of the form x bar, y bar transpose, okay, with two different vectors. Okay, this is a more general model, but I promise that I'm going to kind of lay all of the necessary tools for you to handle also the more general model. Yes.
If I pick a coordinate, the observation will be of size 1 divided by square root of n.
That's right.
So the noise will be very, very big.
Exactly, yeah. Okay. Yeah. So if I want to write this in coordinates, then it means that for each choice of indices I and j, I'm going to observe that thing. So indeed, the noise is order 1 and the signal is very small. But because we have n square observations and only n things to recover, maybe it sort of makes sense. Now, if you pretend that, I don't know how to express this, but okay, anyway, maybe I'm not going to try to explain it, otherwise I'm going to start to calculate information stuff, and it's going to take me time. Other questions on the setup? This is what we observe. The question we want to ask is, what sort of information can we recover about this guy? Okay. Let me see if So for instance, let's say we want to investigate maybe I'm going to write like this. So you want to recover maybe x bar, and you're only allowed functions of your observation. So you're trying to find the best g such that the expectation of x bar minus g of y is small. Yes? What else would you like? You mean, should I write?
The matrix?
Yeah. So you could also consider, yeah, you're right. I'm just, so maybe we could also write this. Indeed, yeah, that's also fine. That's your preference? Yeah, I think it's also a valid thing that you would like to investigate, because this is really what we observe in some sense. So it's just maybe as a warm-up, I was writing this or something. But yeah, this is perhaps a more valid choice indeed, I agree. Okay, so just to say that this is the best G here is the conditional expectation, as we have already said. And so maybe we want to investigate this. So we want to understand how this behaves as n goes to infinity, or similarly here. We want to investigate this. So I should clarify what this sort of absolute value means when I'm dealing with matrices. So let me do this. So in general, during these lectures, I'm going to use, whenever I have two matrices A and B, and I write the scalar product between A and B, I mean you do the scalar product coordinate by coordinate, like entry by entry for the matrices. So I really mean a sum of A, ij, B, ij, okay, for whenever A and B have the same size. Maybe I should write this as a trace of A, B star. Okay, this is my scalar product, and the norm is the associated norm. Okay? So yeah, I would like to investigate this. And when we see this expression, it seems clear that it would be useful to understand the law of x bar given y. Okay, so let's have a look at the law of x bar given y. How can I write it down? So I'm going to write it informally because I think it's otherwise a little bit difficult to follow the calculation if you try to do it more rigorously, but this is a rather elementary calculation, so I'll let you do the rigorous version. So here I'm going to sort of pretend that every random variable is discrete. It takes discrete values. I'm not going to worry about the fact that y is kind of is actually, of course, continuous because it has this Gaussian as an additional term. But let's pretend it's discrete. So I fix some x, maybe in the support of Pn. So I can pretend Pn is discrete if I like. And then I condition on capital Y being equal to y. This is the conditioning, which is a little bit more shaky, but I told you I'm doing a heuristic calculation. If you want to do it still heuristic, but a little bit less ridiculous, you can decide you condition on y being equal to y, or maybe, no, I should say y being around y in a cube of volume dy. Okay, and think in your head that this means your y up to a volume dy. So, well, it's a conditional expectation. So I write like this. This is the intersection of the events divided by the probability of that second event. Now, the probability that x bar is equal to x, by definition, this is, let's say, Pn of x. Maybe I write dPn of x. And then once x bar is chosen, what is the probability that y takes a particular value? Well, x bar is chosen. Then I just have this Gaussian to decide, right? So I can write, if I want this guy to be equal to y, I have to make sure that the Gaussian is equal to little y minus square root of 2t over n, blah, blah, blah. Okay? So this is going to be some constant. I'm not going to write it because it's going to cancel out. Times exponential minus 1/2. So y minus square root of 2t over n. X transpose squared. And then, if you do this calculation a little bit better, you think y is equal to y up to dy. So here I should write dy. Okay, but then it's going to also appear in the denominator, so it's going to cancel out. Okay, so in the denominator, I'm supposed to write the probability that capital Y is equal to y. Well, now that we have done this calculation, it's easy to write down because it's just I can just sum over all possible values of x. So let me write this. So integral dPn of x prime exponential of minus, and again there's a constant here, but I didn't write any of those, so it's fine. Y minus square root of 2t over n x prime transpose squared. And maybe I should write dy again, but I did not write it. So. Okay? So let me set up notation. Just to make my life a bit more agreeable, in this expression, so imagine you expand the square here. So you have y squared minus the cross product plus this guy squared. And in the denominator, you also have this y squared. So if I like, I can just remove it. Okay, so let me remove it. And then I'm just going to keep the cross product. So I get square root of 2t over n y dot x transpose minus t over n x transpose squared. And perhaps let me also make a small comment. There are some, for instance, this term I can simplify its writing if I like. Maybe I could write this as x transpose dot x transpose. And okay, it depends how you like to think about it, but one way to think about it is this transposition operation, it really works as an adjoint. So you could, for instance, play with the game of moving this guy to the left, and so you'll get x star dotted against x star, and then moving this guy to the right, and you'll have x star x dot x star x, and x star x is just the norm of x squared. So really this is just, I could write this as just the norm of x to the power of 4. Okay, let me erase. So I did this informal calculation, but now let me write something which actually makes sense. And that describes the conditional law of x bar given y. Can I erase this? Yeah, we remember that we want to compute these terms, right? Yes, so if I try to write something more rigorous, I would say that for every bounded measurable function g, when I compute the expectation of g of x bar given y, then this is given by the integral of g of x exponential of that thing I just defined, hn circle tx dpn of x divided by the normalization. Whoops. Okay, so this is a statement that does make sense, unlike what I wrote on the right. Okay? And I gave you heuristics for why this is true. Okay? Everybody agrees with that? Okay, so it's interesting. We recognize something that has been put in the form of a Gibbs measure. Well, in some sense, you can always write any measure as a Gibbs measure. But what is nice is that we found a way to write it with an energy function which looks decent, let's say. It looks reasonable. And I think now you can see why I say that this relates to spin glasses. Because this term, if I was writing it explicitly in coordinates, this is sum of yij, xi, xj. Okay, so it should remind you of the spin glass thing. And y is a complicated thing, it's the observation, but inside y it's w plus something else. Okay, so w is really independent standard Gaussians. So this is at least one of the terms hidden here is sum of wij, xi, xj, and wij is standard Gaussian. Okay? So it does look like spin glasses. And in some sense, it looks more complicated, like there are more terms. So why do I claim this is simpler? Perhaps I should first introduce a bit of notation. So let me just pause for a second on this comment. Oops. So this is a Gibbs measure, so I'm going to try to introduce a notation similar to the one we had with Curie-Weiss model to denote it. So for instance, I'm going to, whenever I want to write an integral like this, I'm going to want to write it with the bracket notation as before, like this, like so. Okay, so when I write this, in my head I think that x is a random variable that is sampled under this measure, and the bracket here is the expectation respected to this measure. Does that make sense? So if you like, you can think of this as being shorthand notation for this big fraction over there. Okay? So perhaps you want to object and say, wait, what is on the left side is not that much more symbols than what is on the right side, so why do we introduce yet other symbols? And that's a fair question. The reason I want to do that is that sometimes I'm going to want to write expressions like this, for instance, g of x and x bar. And I don't want you to interpret this as a substitute in there, right? Because there, if I write the, g of x bar comma x bar condition on y, it's not going to capture this. Okay, so when I write something like this, I mean, integral of g of x bar exponential of hn0 tx dpn of x divided by the integral of the exponential da da da. Okay? Does it make sense? So I really want to stress, I think perhaps the more difficult aspect of understanding this new model is to get used to this notation. So let's pay attention. Yes?
The second expression, x bar is a random bar?
Yeah, indeed. Exactly, yeah. Thanks a lot for this point. Let me stress this. So yeah, the novelty compared with Curie-Weiss is that thing, that bracket here, that expectation here itself is random. Okay, because for each choice of x bar and w, you can define this energy function, and it's going to define for you a random Gibbs measure. Okay, and that is that expectation with respect to this random Gibbs measure. You can really compute it for each choice of x bar and w. And in particular, here I'm doing some expectation again for fixed x bar and w. Okay? Yeah, thanks a lot for this point. Everybody is on page with that. So perhaps I want to stress one more time that really, x and x bar are different a priori. Like they really represent different things. Perhaps maybe as a way to, okay, sometimes I like to also write this as integral of g of x dp x bar condition on y x. I mean, you're really sampling x according to the conditional law of x bar given y. Okay, and so yeah, I want to stress one more time that this random variable has a different field than x bar. So if you imagine, for instance, that t equals 0, then if t equals 0, from the observation, you get 0 information about x bar. Okay, you just see nothing. And then the conditional law of x bar given the observation is just the law of x bar. You have not learned anything, so what can you do except just say that this is the original law? On the other hand, if you imagine you have perfect information about x bar, I fully reveal to you what is x bar, and I tell you what is the conditional law of x given x bar, then it's going to be x equals x bar. Okay, so you see on one end of the regime, you have x, which is in some sense a new independent sample from x bar. When you know nothing, you just resample it. And at the other end, x is equal to x bar. Okay, and in between, there's some interpolation. Okay. All right. Yeah, so this is one notation I want to have. And also, sometimes I'm also going to use x prime or x double prime to denote independent copies of x under the measure with the bracket like this. Okay, so people who are familiar with spin glasses will call these replicas, but okay, well, independent copies of x under this Gibbs measure thing. So again, if I want to write this explicitly, what I mean is that if I want to compute the expectation of g of x and x prime. By this, I mean the integral of g of x, x prime. Maybe I could have written this more compactly first. I mean integral of g of x, x prime, and then you sample each according to this conditional law. X bar y x, dp x bar conditional y x prime. If I write explicitly, I mean integral of g x x prime exponential of hn0 tx plus hn0 tx prime dpn x dpn x prime divided by the integral of the exponential of that whole thing. Okay. Again, other questions? So I also allow myself to sample multiple copies of this random variable. We see that they show up later in our calculations.
I'm sorry, but so x bar are the things that we are looking for.
That's right.
But x is like a mute variable.
Yeah, exactly. It's like it's how do you say this? It's an internal variable inside this calculation, if you like. It's like an integration variable. So when you think about this expression, x has no external meaning. Okay, it's internal to the calculation of this integral, and similarly here, it's internal to the calculation of this bracket, if you like.
But so x prime and x prime are mute too.
So yeah, okay. So you can in some sense, when I write this, I mean that you can define a probability measure, which is the probability measure whose density is given like so. And I can sample random variables according to this new probability measure. And I can call them x and x prime and x double prime. And I can average them under this bracket thing, right? And that's what I really mean. But they are consistent with the integral expression, right? So perhaps, perhaps the clearest definition is in formulas is what is written below. So yeah, indeed, in these expressions, x and x prime, in some sense, are mute, like they are internal to the calculation of this bracket. But just like when we calculate expectations of other random variables, we can think about these random variables as what they do inside the integral or something. Are there other questions or?
So here the h also depends on y. So it's like, so do we fix y here?
Yeah. So yeah, exactly. All of what is written here, you should think of it as for fixed realization of capital Y. And capital Y is constructed on top of W and X bar. So perhaps the best way to think about it is for each realization of W and X bar, you can define this object. Okay, so for each realization of W and X bar, you have these laws and these averages and blah, blah, blah. Yeah, so there are two levels of randomness, if you like. There's W and X bar, and then once these are chosen, yet again, you can define this Gibbs measure, etc. Okay, this will be the new ingredient or difficulty compared with Curie Weiss, is that the energy function we are dealing with itself is random. Okay, so yeah, I was trying before to gesture at the fact that this energy function looks like that of the spin glass case, which also has this random energy function. And I kind of tried to sell this model as one in which we have fewer difficulties than in the spin glass case. And so far it perhaps does not look so obvious. We see that in the energy function it looks like a spin glass, but there are other terms. Why should that be better is not transparent. Perhaps one first intuition one can have that maybe things are not going to be so bad after all is that in the spin glass case, things really start to get complicated when you go to the low temperature. It would be like a large T in this language. When the coefficient in front of the W, ij, xi, xj becomes large. But in our setting, because we are doing this inference problem, when t becomes very large, perhaps it's not so bad after all, because if t is very large, maybe we start to understand better and better the actual information, the actual signal. And so in fact, our sample from the Gibbs measure, in fact, wants to be essentially aligned with x bar. And so in fact, it's not doing something crazy because it just wants to align with x bar. Does that make sense? Or in the spin glass case, maybe at low temperature, our Gibbs measure becomes very complicated. We don't know what's going on. But here, when t becomes very large, this Gibbs measure maybe it just wants to be aligned with x bar, and so maybe it's not so complicated after all. Now, this is nice intuition, but how do you make sense of it concretely? And so I'm going to state a proposition, and I claim that this proposition is going to be the sort of tool that represents a little bit the simplification I'm trying to hint at with this informal description. I'm going to erase the board first. Yeah, in some sense, it's that this Gibbs measure it wants to align with something that is already fixed beforehand. Like it doesn't want to go too far away from the x bar guy. Whoops. Yes?
I didn't understand the meaning of the line in the middle of the left ball. This one, exactly. This one was x bar. What is x bar?
X bar is the signal. So at the beginning of the problem, you give yourself x bar and w. Then you define capital Y, which is just a function of x bar and y. So for each choice of w and x bar, you can define this function here, and you can define this average. And if you like, you can also compute averages like this. But I'm just observing that when I write expressions like so, I really mean that you think of x bar as being fixed. It's not being averaged inside the integral. Now, I wrote this just to clarify why I insist in trying to introduce new notation instead of just being happy with that. Because you see, if I try to write something like this using this notation, it's going to be inconvenient for me. Does it make sense? Or?
So after line, it's g of x bar conjunction to y and x bar, and x having the law of x bar conjunction to y.
Okay, I did not follow what you said, but when I write this, I just mean that you think of x bar as being fixed, and you average this guy according to the conditional law of x bar given y. Does that make sense?
But if you substitute this x bar into the definition you have in the line below, they don't really correspond.
This one?
Yeah.
Yes, but here x prime is notation for a random variable. So you're not allowed to substitute for anything else, right? So that's I'm kind of introducing x prime as something with a special meaning. I'm not saying this is a dummy variable with which you can substitute anything. Does that make sense? Yeah, sorry that I told you the harder part is to get used with the notation. Once you get used to it, everything's fine. Elena, you had a question?
I was suggesting maybe replace x with dot, which integrates. The result does not depend on x. Actually, that it's an internal variable. And in the second one also just x with dot. And that means you integrate with respect to that part. And that would probably remove some of the question.
Okay, so maybe that's also an option. But yeah, I like to also write expressions like this with x as being interpreted as the random variable. So, you mean here I should put dot?
No, over there. No, not here. No, not here. On the left. On the left part.
Here? No, here I don't want to put dot. No, I don't want to put dot. I really want to think of x as being the random variable. Just like you call Brownian motion b, and then you say expectation of f of b, and you're like, okay, b is the Brownian motion. If you put dot, you're not quite sure. Anyway, yeah.
Okay, but that would resolve somehow.
Yeah, maybe, but okay. Okay, you have to bear with me. This is my preferred notation. I promise it's good investment, but maybe it's not obvious right now. So I want to display a property which is going to be helpful for us to indeed leverage the fact that this model is simpler than the spin glass case. And yeah, I wanted to spend time on making sure we understand the notation, because this property I'm going to write down now really is kind of a play around these definitions. So perhaps before I state the property, I could make a comment. So just to continue playing with this notation. So now we have this quantity g of x averaged under the Gibbs measure. So as we have discussed, this is still a random quantity. It depends on x bar and w. So I can take its expectation with respect to these guys. Okay, and this is, and by definition, this is the same as this, which is the same as the expectation of g of x bar. Okay, so I stress that this thing is not the same as that bracket, but after you take expectation, they give you the same thing. Okay, remember the example of sometimes you should think of x as being equal to x bar, sometimes you should think of x as being an independent sample from x bar, and in general, x is something in between these two cases, but it satisfies this property. Okay, and now I want to extend this and say that in fact you can make this sort of substitution in a slightly marginal setup. So let me write this. Let's say for every bounded measurable G, if you average over really everything, like the double average, maybe I'm going to write this guy, then this is the same as if you're allowed to substitute this x prime by x bar. Maybe I'm going to write like this. Okay, and similarly, I can, okay, maybe just to give you, okay, maybe I don't write the more general statement. All right, so let's again consider that. I hope I convinced you that before you take the expectation, these two things really are different. Okay, and now similarly, I want to make sure we agree, first of all, that before I take the expectation, that thing, that bracket and that bracket are different. I hope you can see that, okay? There is one written here, another one written there. They are genuinely different, okay? But the claim is that if you take the expectation, they get the same value. Okay, okay, there's a kind of intuitive way to see this, but okay, I prefer to give a careful proof, let's say. So this is called the Nishimori, oftentimes this is called the Nishimori property. I'm not sure if this is a great name, but we're going to call it like this. Okay, you can generalize this to having more copies, and the point is that you can always substitute one of these guys into the x bar. But I'm not going to give you the full statement. All right, so how do we prove this? So this is a statement for every bounded measurable function. By some monotone class argument, it suffices that you restrict to the case when g is a product of two functions of one variable. Okay, so let's say by monotone class, or maybe you prefer to call this pi lambda, monotone class argument. So I'm writing the product case. Maybe I'm going to call it F, okay, but we don't mess it up with the free energy. Okay, so instead of this general form, I'm going to only restrict to this form. Yeah, and I want to show the result for this function, and then you can extend by standard arguments. All right, so let me try to work on this. What should you do? Yes. So these are independent copies under the bracket. So if I want, I could write it like this, for instance. Okay, we're just continuing to do gymnastics around this notation to make sure we understand what it does. Maybe after the hike, gymnastics is not the good thing, but okay, we can still handle it a bit. So by definition, this bracket, I can rewrite it as this conditional expectation. And now the key point to observe is that our bracket average, as written here, okay, it depends on W and X bar, but in fact, it's really only a function of Y, of the observation. Okay, and so this is Y measurable. Okay, so if I like, I can insert it inside this conditional expectation. Okay, and again, if notation feels confusing, think that I'm just writing explicitly this integral. Okay, imagine I'm writing explicitly the ratio of integrals, and there's just a y inside. Agreed? And now I'm in pretty good shape because, from the point of view of this Gibbs measure, I told you I consider that x bar is a fixed variable. So if I like, I can insert it in there. And of course, by the Tower property of the expectation, this I can remove. So you see that this completes my proof, in fact. Okay, that was what I wanted to show. Okay, and you see the key point is that the Gibbs measure is Y measurable. Okay, so to continue to stretch our muscles around this notation, let me give you an example. I said that it's one of the things we would like to compute is this difference squared. Maybe I should have called it the minimal mean square error. And so if I like this, I can rewrite as expectation, like a bracket x. Okay, and so then if I expand, this is expectation of x bar squared minus 2 times expectation of, too many bars, x dot x bar plus, maybe I don't have enough space here, plus expectation of bracket x squared. Agreed? Maybe I'm going to rewrite bracket x squared like this, bracket x dot bracket x. Okay. So instead of writing bracket x dot bracket x, I could also write one bracket and then just x dot x prime. Right? X prime is made for that. It's just an independent copy of x. And now I can appeal to this Nishimori property, the fact that when I have this double expectation of x, some function of x and x prime, if I wish, I can replace one x prime by x bar. By the way, in the proof, I assume the function is of product form. Actually, here the function is of product form. Okay, so if you don't like a monotone class argument, you just ignore it. It's okay. And so this term, in fact, is the same as this one. So what we get is expectation of x bar squared minus expectation of x dot x bar. Okay, so this is a simple term to calculate, the first term. This is just sum of expectation of x bar I squared is just n times expectation of x bar 1 squared. Okay, so it's just a completely simple term. And so really what we need to understand, if we have this kind of Gibbs measure thing in our head, is how does the scalar product between x bar, the signal, and x, in some sense, our representative for the best guess of what x bar is, how does this behave as n go to infinity? Is it the case that we manage to have x align very well with x bar? For instance, if x is equal to x bar, that would be very nice. Or is it the case that we don't manage to align it very well? For instance, if x is just an independent resampling of x bar, then this is not going to work very well. So, in some sense, this is the sort of quantity we are going to focus on studying. Okay, the behavior of this scalar product between a sample of this x, a sample from the conditional law of x bar given the observation, and x bar itself. Okay, and maybe I'm going to also record that, as Olivier was pointing out, maybe it's more sensible to focus on the minimal mean square error for the matrix, and you can do the same sort of game in this case as well. Okay, this is bracket of x bar, of x transpose, and you can just write the exact same thing. In fact, it's just every time you have written x or x bar, you write x star or x bar star. Okay, so it's exactly the same calculation, and you get expectation of x bar transpose squared minus expectation bracket x bar, maybe I write x transpose dot x bar transpose. Okay, exactly the same calculation. And again, if you like, you can rewrite this as, you do these interchanges as before. You can write this as x dot x bar everything squared. Okay? Yeah, so this you can call the overlap between our Gibbs sample and the signal. Yes, it did, and this feels more like the overlap. So depending on, I don't know, one's point of view, one can think this looks simpler or this looks simpler. So for instance, from the point of view of you're doing your calculations and you're scared that there will be too many of these Gibbs copies you don't understand very well, maybe you prefer to write this. But from the converse point of view, if you think that you're the statistician and you try to understand x bar and you don't know it, but maybe you can create samples, x and independent copies if you like, it's kind of remarkable that at least at the level of expectations, you can know how much you overlap with the truth by just sampling two things according to your conditional law. So depending on your point of view, you can prefer to have one expression or the other. If that makes sense.
Second question, is there any equivalent of Guérin-Laguerre identity for this stuff?
So in fact, because of this property, we will always be replica symmetric. So the overlap will always be concentrated, so we don't need to worry too much about aspects like so, but okay, that was a technical point. So I hope I convinced you that it will be, so anyway, I introduced new notation to talk about these minimal mean square errors, for instance, and we want to study their behavior as n goes to infinity. And I kind of try to advertise that in general, when we face these problems, which maybe are nicely encoded in this language with Gibbs measures, the natural first step is to try to calculate the free energy. So maybe also here, we're going to try to do that and see what happens. Okay, so perhaps we want to calculate, just like with Curie-Weiss, maybe this is not the first quantity we absolutely want to understand, but we hope that by understanding this, maybe later by studying derivatives, we will also understand the quantities that we mostly care about. So in our case, if I write the free energy as it comes for us, I'm going to write something like this, 1 over n log integral of exponential of hn0 tx dpn of x. Okay. So again, as we have stressed earlier, one key difference between this problem and the problem we faced earlier is that now this is a disordered model. This free energy itself is random. Okay? This quantity here has some w and x bar hidden inside. So I can define this, but I can also define its expectation. I'm going to write fn bar 0 of t, the expectation of that quantity. Okay? And we're going to see soon that when I differentiate in t this expression, I get indeed something that is of interest to us because I get this scalar product between x and x bar squared. Okay, I'm not going to justify this immediately, but I'm going to justify this soon enough. But what I want to say here first is, what do we do next? What is our next move? Let's suppose this is true. What do we do? We are here, we are standing there, this is our problem, we want to study this function, we have calculated the derivative, we have found this, and then what? There is only one variable, so what can I do? Maybe I should take more derivatives, but if we try to do that, we're not going to find anything that looks remotely sensible. So what's our next move? And in order to understand what's going on to us right now, I would like that you try to imagine that we study the standard Curie-Weiss model, but we have forgotten to add this h parameter. Maybe not forgotten, we just have not done it. Maybe we don't care about this at first. We just start and we study the Curie-Weiss vanilla. Let's say there's just T over n, sum of sigma I, sigma j. We define our free energy, and then what? So in fact, I kind of immediately splashed it onto you, this extra h. But perhaps the first task that you need to resolve is, what are the extra quantities I should add in the energy function so that when I compute the first derivatives, I get something that works nicely. I can find plausible relations between the derivatives with respect to the different parameters. And here, we have not yet done our extra addition of the good parts of the energy function. We just have maybe the core part, which is the one which mostly interests us, but we have not added our h extra friendly variable. And this extra piece, it needs to satisfy two things which are a little bit in tension. One is that, well, we would like that as we differentiate with respect to this extra parameter, we get relationship with the derivative we care about. So for instance, it would be nice if when we differentiate with respect to h, we get just the expectation without the square, for instance. That would evoke what happens with Curie-Weiss. But on the other hand, we don't want to make our problem too complicated, because if we add things that are extremely crazy, then what can we do? So we would also like that we add things that are relatively simple. And for the Curie-Weiss, the kind of signature of the simplicity was that the part with the h was, in some sense, there was no interaction between sigma I and sigma j inside this term. It was just sum of sigma I. And so in particular, when we were setting t equals 0, it was very simple to calculate the free energy. Okay, so here I want to satisfy these two competing requirements again. It's kind of rich enough that I can relate it to the t derivative, but it's also simple enough that if it's at least, if only this part is in the energy function, I can compute the free energy. Make sense? So perhaps, if I want that when I differentiate in h, I get x dot x bar over n, perhaps what I could do is just take my current energy function and then just add, maybe hn times x dot x bar over n. Maybe I could just do that. But there is a disadvantage to doing this, which is that I kind of try to promote this property that I call the Nishimura property. which really comes from the fact that we are solving an inference problem. I sold this as an important ingredient for simplifying our problem, the fact that we are trying to infer a particular signal. So in this context, on top of these two requirements, I want to also make sure that I do not destroy the property that we are trying to recover a signal. You know, I would like still that my Gibbs measure, even after I change the definition of the energy function, I can still think of it as, yeah, it's the conditional law of something given the observation. Okay, I want to keep that property still around. Okay, so instead of brutally trying to insert whatever I want inside the energy function, I'm going to just imagine we're observing something else about x bar and something else which is simpler, and this will define for me a new kind of more general statistical inference problem, which hopefully will have this extra variable around and maybe will make my life simpler. Does that make sense? So that is it. So we want to add a new, we want to enrich the problem, let's say. I'm not going to rewrite all the discussion I said, but let me write just to add a friendly h, you know, something like this. Without breaking the fact that we are, that the Gibbs measure is a conditional expectation. This was really the ingredient in the proof, you know, that the Gibbs measure is the conditional expectation. So to implement this, I'm going to postulate that on top of this observation that we were calling capital Y, we also observe the following thing. Let me call this Y tilde. So now instead of this complicated like pairwise interaction term, I'm just postulating that we're observing directly a noisy version of x bar. Okay, so this is Z is so this is letter Z, and this is just a vector of standard Gaussians. And H is a parameter just like we had T before. Make sense? So now I'm considering a more general statistical problem where I would like to recover x bar, or maybe the matrix x bar transpose, and I observe both this capital Y we had already, which I have not kept on the board, and also this Y tilde. Okay, so now we observe. So in total, we observe. Let me write this calligraphic Y, the pair straight Y and Y tilde. Okay? Once you have decided this is what you want to do, you can kind of reproduce the calculations we have been doing. So you can still write the conditional law of x bar given this more sophisticated observation. It's really a very similar calculation. So similarly as before, let's say. And that is why I was writing this Hn with a 0 on top, because it was not yet my preferred definition for Hn. So now it will depend on T and also on H. So there's the first part, Hn0 of Cx. Maybe I should rewrite it explicitly. Maybe rewrite it explicitly. Maybe it's best if I look at my notes, but I'll try to do it like this. So that was our first guy. And now we have also the H part. And the H part has exactly the same structure. Each time you had a quadratic term, you just write a linear term now. Okay. So perhaps you remember that y is the sum of square root of 2t over n, x bar transpose plus w. And y tilde, you have the definition on the board. If I really want to make things very explicit in terms of this original randomness, I can write the full formula, so maybe I'll do it. So this is equal to, all right, so let me do that. So square root of 2t, so inside this there's a w, maybe I'll start with that. Square root of 2t over n w dot xx transpose. Then inside here there's an x bar. So we get plus 2t over n x bar transpose dot xx transpose minus t over n xx transpose squared. So that's the first line written in full, in its full extension. And then the second line I can do the same. So plus square root of 2h z dot x plus 2h x bar dot x minus h x squared. Agreed? Okay, so really this should evoke to you the spin glass guy. Okay, this is sum of wij xi xj. Okay, for some reason instead of sigma I wrote x, but other than that, this is the energy function for the SK model I talked at during the first lecture. And this also, you can think of it as a sort of spin glass, sort of external random magnetic field. Okay, so this really wants to look like a spin glass. And this part is here because we are doing this statistical inference problem, and in some sense you should think of it as being terms that are here to help us to make sure this Nishimori property is valid. Okay, so let's say here to help. Okay, so they look scary, but in fact they are good. Okay, so perhaps one thing you may be wondering for a while now is, why did I put square roots in front of the parameters? Maybe, why not just write 2t instead of square root of 2t? And one first way to try to justify this is you see that they really are kind of pairing with this Gaussian noise. And so, square root of t times the Gaussian should evoke to you a Brownian motion. And if you want to, so it kind of makes sense that you want to add the variance linearly as you proceed. And yeah, I still have this on the board. Well, we have not yet justified that this property